Okay, so the first question is, if you are looking at a Turing machine where the tape is a two-dimensional tape. So here, just 1 minute. So here on the left hand side you have, look at the first cell on the left hand side, you have left hand markers in each of these cells, in each of the rows. And so this could be some special symbol. And on the bottom row, each of the elements are marked with a bottom end marker. Okay, so you know where to stop towards the left and where to stop towards the bottom, but you can move infinitely to the right and upwards. And your moves are so delta p a will be of the form q b and some d, and this direction can belong to left, right, top, bottom. Of course, you have to ensure that if A is the left hand marker, then this D should always be R or T. R, T or B cannot be L. And if it's the bottom end marker, if A is the bottom end marker, then D should be, D cannot be B. It could be any of the other three. Okay. And okay, if it's this special left and bottom end marker, then it can only be top or right. Okay, so now you have to prove that this Turing machine is equivalent to a traditional Turing machine. Of course, one direction is true. If you give me a Turing machine, traditional Turing machine, just in the bottom or in the tape just above this. So if this is row 0, in row 1, I will be able to simulate everything of the traditional Turing machine. Now, if I give you a two-dimensional Turing machine, can you show equivalence to a Turing machine? So the language that a two-dimensional Turing machine is accepting should also have a traditional Turing machine accepting it. Okay, how will you proceed? So what do you have to show basically? So, suppose I can give a bijective function f from n cross n to n. Then will I be done?
Yes, ma'am.
Why?
Ma'am, because for this n, we can always form a single Turing machine, a single tape Turing machine.
So basically you're flattening this entire region,
Yes,
right?
ma'am. Yes,
So
ma'am.
what can be a bijective function?
Thinking, ma'am.
So basically you take some ij and you have to position it somewhere. You can give me some exponent, I mean the f can map to something exponential in ing also. First, let's try that. So we saw something for counter automata. Can we use similar ideas? Or any other bijection function? Okay, so I'll leave it to you to find this bijective function from n cross n to n. But the idea is if I have this, then I will have converted this into a single tape. So every ijth, whatever is in the ijth content, I will look at I look at the fijth cell. So this is the simulation of this two-dimensional Turing machine by a traditional Turing machine. So let's look at the next question. So now I have a queue automaton, which means I have a finite control, and then I have a queue. So in a queue, you are popping out the first element and you're pushing in something at the end. And the question is that if you look at a queue automata, that is equivalent to a Turing machine. So this is similar to a PDA. You have a read-only input tape where you're writing down your input and you can only move right to the right. It is possible that you stay stationary at some point. That is your equivalent epsilon transition, similar to how you defined for PDAs. But you can only move right. You cannot move to the left. And you have some states in your finite control, and you have a queue. As your external memory, you have a queue where a queue is um, first in, first out. So you bring out from the first element is popped out, and the new thing that you put in is pushed to the end of the queue. So how will you show that this is equivalent to a Turing machine? So can you give me one direction? If I have a queue automaton implies Turing machine, meaning that if a language is accepted by a queue automaton, it will also be accepted by a Turing machine. Can you give this? How will you do this? So suppose you have a three tape Turing machine. It's enough to show that a Q automaton can be simulated by a three tape Turing machine. So in the first tape, you write down the input. In the second tape, you are basically going to keep content of the Q. And third tape is for writing down transition. That you want to apply. Okay, so basically here is your input. Here is this is a tape that keeps the content of the queue, and this is what you have to update. And here you've written down some transition, let's say some alpha goes to, I won't say alpha goes to beta. Some Q A goes to P B. So now what will you do? How will you simulate this? Oh, sorry, just one mistake. This is going to be of this form. QAA goes to some P beta, let's say. Yeah. How will you simulate this? Okay, Abhay Kumar Keshari, are you here?
Yes, ma'am.
How will you do this? So currently you are at your finite control has Q. You are at state Q and your tape head on your input tape is reading A. And suppose the first thing that you're seeing is A. So that's why you are writing QAA going to some P beta. Now over here, what would have happened? You would have taken A out, pushed everything. So the first element would have been the element right after A, and you would have pushed in beta, changed from Q to P, and then gone to the next alphabet or stayed at the same alphabet. So now what do you do? How do you simulate this here? What does popping A mean? How are you going to pop A?
Can we override each element by the one right on its right side, and then when we encounter a space, we'll put a B there?
Okay, so basically you're saying move everything to the right first. You remove
Left.
A and move everything to the right on this step.
No, to the left. One step. Everything
Sorry,
to
to the left, to the left, to the left.
Yes, ma'am.
Then once you encounter a blank, this is where you start writing beta. You start
Yes, ma'am.
copying. So
After
here,
copying only, then first time we'll have to copy the blank also. Like some character will be. Yes, ma'am. The last character will be overwritten by a blank,
by a blank,
then
right? Now you
and then
come to
that
the
blank will be
left.
overwritten by beta.
Now you come to the left and look for the first blank.
Yes, ma'am.
Now at the first blank, you copy down beta, and you can think of this as some, let's say, Q hash A hash A hash P hash beta. So you somehow mark the fact that I have to start copying after this marked hash. And then you write this beta down starting from the first blank space on the second tape. So fine?
Yes, ma'am. Yes, ma'am.
Okay. Okay, so one direction is clear. Now you have to say that look at a language that is being accepted by a Turing machine. You have to show that it is accepted by a Q automaton as well.
A queue is basically two stacks. Like we can, like a queue can be seen as two stacks. So, and we know that that a two stack PDA will be as strong as a Turing machine. So,
How exactly are you seeing a, because see, this is I mean I've drawn the queue like this, but a queue has a starting point. Maybe I should draw it like this. Q has a starting point. I mean, I know what my first element is. I cannot add anything here. So how are you thinking of this as two stacks? Were you thinking of breaking it up somewhere?
yes, ma'am, I was thinking something like that.
But then two stacks, Q is not exactly two stacks, right?
Yes, ma'am.
Okay, but the idea is in a Turing machine, basically you just have to, the finite control you can remember in the finite control of the queue, whatever's happening in the finite control. You basically have to remember what is happening in the tape of the Turing machine using your queue, right? And your tape will have something written on it. In particular, you can also think of it as, I want to remember my current configuration. So we saw how to encode a configuration. The first configuration would be S, left hand marker, W, and I'm just putting a right hand marker to be safe. Right hand marker is the last element before I have blank spaces. So this encodes all of the content of the tape I have seen, as well as what state I am at and where my tape head is. So at the beginning, the tape head is at the left hand marker on the tape, and therefore I have to write this, I indicate this position by writing the current state just before the symbol where the tape head is. This is how I encode my configuration as a string. So now all I need to do is remember these configurations of the Turing machine. So suppose after this I apply ds left hand marker is equal to q left hand marker right. Okay, so then my next configuration becomes left hand marker q w right hand marker, right? And I keep doing this up to a certain point when I have left hand marker, maybe some W1, then T, which is my accept state, then some W2, and then the right hand marker. I always maintain the right hand marker after like the last non-trivial element is the right hand marker. Let's assume.
What is QW?
W is, so I am just applying in one step the next configuration from the start configuration on application of this transition will be this, right? Because on my Turing machine, I have moved the tape head one step to the right, and I have transitioned from S to Q. This is how I encode configuration in terms of a string. Is this part clear? Any questions regarding this part? Okay, so let me give you a gist and then you can work out the details. The basic idea is in my finite control. So I will try to think of this as my Q. I have this as my Q. Q. And I will have two positions. Maybe I'm remembering it in my finite control. I will have two positions which I am going to remember in the following way. So basically, this position, the rightmost, the right hand side of this position will store the current state, and then there will be some alphabet C before this, and the leftmost element of the Q will denote the alphabet that my tape head is reading, and then you have the rest of W, and then you have the right hand marker. Maybe then you'll have the left hand marker and then something more. So basically I've wrapped it around. If you look at the current configuration, I've broken it up. I am basically looking at, so over here, these are the two things that I'm remembering in my finite state, and W onwards, I'm remembering on my Q. Now in the next step, at a certain stage, if my configuration is, let's say, W1, Q, A, W2, and right hand marker, then this is what I'm going to be remembering in my finite control. Sorry, not this. Let me rewrite this a little bit. I have W1, C, Q, A, W2, right hand marker. So this is what I will be remembering in my finite control. And starting from A, so A will be the first element on my Q. But I have to remember this, so I just remember these things at the end. So you can think of this as a circular way of reading things. Okay, you start from A, after your right hand marker, you read the left hand marker and the rest of W1. Now I have given you the data structure. Now my question is, how will you simulate a right move? So suppose you are seeing delta QA is going to P, B, R. How will you simulate this? So I know if I look at the rightmost element, I mean, if I should maintain the invariant that the rightmost element on my in the small space which I'm remembering in my finite control, the rightmost element will be the current state, and the leftmost element on my Q should be the current alphabet on that my tape head in the corresponding Turing machine is reading. Now, if I have delta QA where Q is going to P, A is being rewritten by B, and I'm shifting to the right. So then what happens? What should I do over here to maintain the invariant that my current state should be on the left hand side, should be on the right hand side of these two positions, and my current input, the current tape content that my tape head is reading should be on the left of the queue.
We can pop A and push B.
Pop A, so you pop A out and you push B at the end.
Yes, ma'am.
Okay, what are you doing here?
Ma'am, actually, that part I did not understand. What is that on the top? Like Q.
So okay, so this is the idea that I have a configuration. Let's call this a configuration, current configuration. Now the idea is that I have to understand what the current, in order to apply a transition, I have to understand what is my current state and what is my current alphabet, right?
Yes, ma'am.
Right. So what we are doing is, in the finite control, I can remember the current state and maybe one alphabet before this. And in my queue, I will always maintain the fact that the element that is to be popped in the queue is the element that is being read in my Turing machine. So because this is the place where I am doing the rewrite in my Turing machine tape.
Okay, ma'am.
So this is why W is the place where I can make a change in my queue, and W is the place where I can make a change in my Turing machine. So I have to make sure that W is the first element on my queue so that I can pop it out and maybe, but in my queue I can only write it at the back. So therefore this circular structure that we have to maintain. I cannot read it in my Turing machine. Okay, let me add a page. In my Turing machine, suppose in my Turing machine, so let's look at okay, wait, I don't know what's. Let me open a new thing. Okay, so in my Turing machine, let's say I am at a particular, my current configuration is W1, the element just before is C, then I'm at state, let's say Q, and I'm reading A at the moment, element right after that is, let's say C2, and then I have some W2, and then the right hand marker, and everything after that is blank. Now in a queue, what you have to do is, in a queue, it must, you can only do, in the tape, you can only do a rewrite at A. In the queue, you can only do a rewrite at the first position, and whatever you're rewriting must be entered in the last position. You pop it out and you enter it in the last position. So notice that, suppose I am applying the transition delta QA is equal to PBR. Okay, then this becomes W1 C B P C2 W2 right hand marker. But here if I just wrote down everything, so in the queue, suppose I had A, C2, W2, right hand marker. And okay, I don't exactly know how to place this yet. But if I popped out A, I have to enter everything at the end. I cannot replace A. In the Turing machine, I was replacing A. So instead of looking at the Turing machine as left to right, what we are doing is we are looking at it in a circular fashion. So if I'm reading A, I read everything after A is C2, W2, left, right hand marker. Then you go to the left and you read everything from the left hand marker W1, CQ. Now I have to remember these last two things. I have to remember what the state is. So just to be careful, because I also need a left movement. In the left movement, I will have to change C in some manner. That's why I'm remembering the two elements just before my tape head separately in my finite control, maybe using some state. Okay, so I remember CQ. Now if I have to make this transition, so what happens? I have to basically store this using my finite control and using this tape. Now the change that happened is, instead of CQ, now I have CB, right? So I popped A out and I should push B somewhere. So what I do is I write, instead of this, I change this to BP. I popped A out, so my first alphabet is C2, W2, right hand marker. I instead of this, I made this, I remember BP instead of CQ in my finite control. So up to here I have left. Now in my actual, so what did I have? Over here I had W1, right? So I have W1 after this. Now what do I have to remember? I have till BP, I just have to pop in C. So if you look at this configuration, the corresponding state in the queue is as follows. In my queue, I have A, C2, W2, right hand marker, followed by left hand marker W1. And this portion is remembered in my finite control or in my states. Now, when I make this kind of a transition, my configuration changes to left hand marker W1, C, B, P, C2, W2, right hand marker. My invariant is the first element where the tape head is should be the first element of the queue, and the rightmost element in my that I'm remembering in my finite control should be the state I am at. So these two elements I'm remembering in my finite control. Instead of CQ, now I remember BP. What is the, once I do this, what will my Q read if I do it in this circular fashion? C2, W2, right hand marker, left hand marker, W1. This is the same after A, this is what it was. Now the extra thing that has to be remembered is this C, which I push in. Is it clear?
Yes, ma'am.
Okay, now I want you to see what happens if the transition is of this form. This is the first thing. And the second thing is, what happens if the transition is of this form? Something, some direction, L or R. Okay, so these are the two things I want you to look. So basically you have to look at your configuration, the next configuration, and figure out how you will manipulate your queue so that it stores the next configuration, and you're always reading in a circular fashion. You start reading from your from the alphabet that is being read by the tape head, move rightwards. When you hit the right hand marker, you come to the left hand marker and move rightwards till you hit the alphabet just before the alphabet being read by the tape head. The alphabet just before that and the state is being remembered in my finite control just for ease of computation. Okay, so I want you to try this on your own. Let's go to the next question. Okay, so we saw the non-deterministic total Turing machine for testing compositeness. So if I give you an a to the n, and I want you to check whether n is composite or not. We had the test, right? We copied down a's up to a certain point, let's say some m, and then we checked whether there are so we kept marking a to the m length strings onto a to the n, and we checked whether everything got marked or not and whether we were trying to mark any blank space. If not, then n is divisible by m. So basically we have guessed a factor of n and we are checking whether that is a factor or not. Now the question is, what in the non-deterministic Turing machine, what is the running time of this? So in a configuration, so in the first step, which is copying A's, and second step is checking multiplicity of A's. Of copied A's with a to the n. So what is the running time of each of the, say, how many it basically means what is the worst number of configurations you are moving through for the first step and then for the second step. What about the first step? What's the worst number of configurations you can go through while copying A's? So Anirban Haldar, are you here? Anirban Haldar? Gadde Gayatri? Oh, okay, sorry. Venkatesai, are you here? Venkat Sai, are you here? Spandan Haldar? Rupak Priyadarshi?
Yes, ma'am.
Yeah, so what is the first step? For the first step, when you're copying the A's, what is the worst time? What are the worst number of, what is the worst possible number of configurations you go through while copying A's?
N configurations.
Right. So the amount of time, the worst amount of time you require for the first step is n, right? Because you can copy at most n A's. Okay, so after the first step, in the first tape you have a to the n written, and in the second tape you have a to the m written, and you have to check whether, so you keep marking copies of a to the m, and you check whether n can be completely covered in this way, right?
Yes, sir.
So what is the time complexity for this in the Turing machine? How many configurations do you have to go through?
N square maximum, like
N square. Why?
for checking each A, means each A against N.
No, so what are you doing? Basically, you this A to the M, you read an alphabet here, you mark an alphabet here. Then you read the next one, you mark the next one. Till you hit a blank, right? If you hit a blank, then over here you have marked M A's. Next, you move to the right, you read an alphabet, mark an alphabet. Read an alphabet, mark an alphabet. Keep
Okay,
doing
so
this.
maximum would be N, I think.
N or N, right? 2n, right? Because I'm no, n, right. Okay, so the running time for this is 2n. In the worst case, so look at the longest path of configurations in your tree of configurations. The longest path can be of length 2n, at most 2n. Fine?
Yes, ma'am.
Okay. Okay, so let's go to the next question. You have to design a non-deterministic Turing machine to accept the language W reverse W such that W belongs to AB star. So in your,
But ma'am, in the previous question, 2n is for checking for one particular m. Like we'll have to check for all up to something like square root of n or something.
no, right? So that's the power of the Turing machine. So what you're describing is a deterministic Turing machine where you have to check up to square root of n to see whether one such factor exists or not. But in the non-deterministic Turing machine, the running time consists of one run. So one run is you copy A's and you stop copying A's at some point. You guess where you want to stop. Okay, this is your first
Yes,
step. Now in the second step, you check whether for the number, suppose you've copied m A's, you check whether m divides n or not. Meaning whether you can cover n with m copies, with copies of a to the n. If you can, you say yes. If you cannot, you say no. The idea is that if a factor exists, there exists a path where you will be saying yes. That's all you need. Right? So your non-deterministic Turing machine is doing just this. It's not going through all possible copies of A. It is guessing up to an A. It is guessing an M for which you have copied A to the M, and it is checking whether M divides N. Now if M divides N, you say yes, otherwise you say no. So wherever it is guessing, at some point you have so you have some branches, wherever it's guessing. I think it will be better if I do an exact version of this. So you have the start configuration C0, and then either then the first steps are you copy 2 copies of A. So you have C1 and C2 where you copy 2 copies of A. If you don't, then C1 and C2. If you cannot copy 2 copies of A, then C1 and C2 will be where it ends. Otherwise, if you can continue, then you have two choices. Either you copy another A or you start your step 2. So this is copying another A. This is start step 2. At C3 also you have two choices. Copy another A, step 1 or step 2. And so on. And C4, after step 2, you have different configurations. You have a path where you're checking whether it is divisible or not. At the end, you are saying yes or no. At this leaf, you're saying yes or no. Similarly, over here, at some point, you will decide to go to step 2, after which you have a path, at the end of which, at the leaf, you're saying yes or no. So the time complexity of this machine, of this NTM, is basically the height of this tree, not the total number of configurations in the tree.
Okay, but the Turing
Yes.
machine does not know which path to take, but whatever path it takes, it will be at worst order n.
Yes.
Like, is that
Right.
the idea?
That is the idea. So
Okay.
height gives you the longest path, right?
Yes, ma'am.
So you are basically trying to see what is the worst number of configurations you can go through. Turing machine does not know. So a Turing machine's run is basically a sequence of configurations. What is the worst length of that sequence? That is your running time. That is the upper bound on your running time for that non-deterministic Turing machine. Fine?
Yes, ma'am.
Okay. So I'll move to the
Uh,
next question. Yes.
So for the deterministic Turing machine, this same running time would be of order n square.
Yes. Can you explain why?
For this, we will like add for all the m smaller than n.
Right. So this thing you will try for each of the n's. Each m up to n. And for each of them, you will take some running time n.
Okay, thank you.
Yeah. So in deterministic Turing machine, basically you are multiplying in because the first step you cannot guess. You have to try everything. In non-deterministic Turing machine, since you have the option of guessing, you are adding this. That's why it's coming to 2n. You are assuming that for some run, I am doing the first step correctly. Fine?
Yes, sir.
Okay. Okay, so next question is design a non-deterministic Turing machine that accepts the following language. You can assume you have a right-hand marker. How will you do this? Non-deterministic Turing machine. So just to be clear, you don't know what W is. You are given some string X and you have to check whether X is of the form W, W reverse W. So first sanity check is whether the length is divisible by 3, right?
Yes, ma'am.
Okay, after that, Okay, so actually, I'll take this.
Can we just divide the string into three partitions, like into three parts arbitrarily, and then we'll check if this thing holds. Like, is it of the form W, W reverse W?
So you're saying arbitrary 3 parts.
Yes, ma'am.
So basically, I'm assuming that you also have a few more.
Tapes.
You have, let's say, 3 more tapes.
Yes, ma'am.
So you're saying after a certain point, so I keep copying. What I move on my first tape. I move rightwards.
Yes, ma'am.
I keep copying. So let me copy up to x1 and then I stop. Then I keep
Yes, ma'am.
copying
Then the remaining part.
x2. Then I stop. Then
Yes.
I copy the remaining thing and I'm done. Now the objective is to check whether these two match and whether this matches in the opposite direction.
Yes, ma'am.
Okay, so what's the time required? So you can assume that parallelly you're moving all these heads.
Like let's say the length is L, and like we are choosing any two characters to break it, right? So LC2 something, and then we'll take order L time to match again. So order L
1
cube.
minute, LC2.
No, like we are splitting it into three parts, so we are arbitrarily choosing any 2 points. So how many choices are there? I was trying
That
to
doesn't
find out.
matter, right? You're arbitrarily breaking into 3 parts. You don't have to make
Okay,
choices.
again,
You're
okay.
guessing, right?
Yes, ma'am. Okay.
So how much time? That's why I said you keep copying up to a certain point, then you decide to switch to the to the third tape. Keep copying. After that, you decide to switch to the fourth tape. So this is
So
where
order
you're.
L time to L, it like to copy the whole string will take L time.
Okay, so this takes L time and this match as necessary
Again L time.
L time. So again,
Like
I'll
order
just
L
write it
time.
as order L.
Yes, ma'am.
Okay. Okay, so this is where the non-determinism is coming in. You are breaking this arbitrary. You are guessing the 3 parts. So instead of
Yes,
saying
ma'am.
arbitrary, I say guess 3 parts. Okay. Okay, so there are 2 questions. I leave this one. This is a little bit technical. For the 6th question, so now you have a Turing machine that it's a two-way infinite tape. This Turing machine has a two-way infinite tape. You're starting at some position. So all cells are blank. This is a special variant. All cells are blank except for one position which has a hash symbol. And the objective is to locate this hash symbol. So you are at some point. So the first question is, if it's a non-deterministic Turing machine, what is your strategy? If it's a deterministic Turing machine, what is your strategy? And time comparison.
And if it's a deterministic Turing machine, we can split the thing into two parts and from anywhere, and then we'll write the same thing like in two tapes, and then both the tapes will move parallelly, so that.
But you can't, right? Here there is infinitely many, here there is infinitely many. So how will you copy this entire portion? You will keep copying, right?
Okay, right.
So think of it this way. This tape head can either move, so this hash can be either be on the left hand side or on the right hand side of the start position.
Yes, ma'am.
So if I knew the direction, what would you do? If I knew that my hash would be on the right hand side, what would I do?
We'll just keep moving left till it appears.
Right, right. Okay, now can you give me a non-deterministic Turing machine?
I mean, we'll assume which direction it is in and
Uh-huh.
then keep moving.
So guess the direction of hash and keep moving in that direction. How much time will it take?
I'm guessing we'll take constant time, like
Huh.
no time. But
Yes.
if we make the wrong guess, then it will be infinite.
Huh. So this can take you can keep going. And if you make the correct guess, then
Again some time, like not infinite, like finite time
so
probably.
suppose from the start position, if this distance is L, then
Then
L time. Okay. Now let's go to deterministic Turing machine. What will you do? I don't know. I cannot guess, right? If I move in the wrong direction, I will keep moving. But can I do something better?
Yes, ma'am. We can move one to the left, then again like three to the right, then
3 or
something
2
like
to the right.
two to the right, yes.
Ah.
Then three to the left,
Ah.
and so on. So
Okay.
we'll explore both sides.
Okay. So you're moving 1, then 2 to the right, then 3 to the left, then again 4 to the right, and so on up to
L.
L or
Hmm. Okay, no.
you're right. What is the what
2L
is
plus 1.
right up to 2L plus 1. So how much is this?
Order L square. Like
Right. This is order L square. Okay. So see, if you are making a correct guess, then notice that my non-deterministic Turing machine is doing way better, because here I'll take order L square time. But if
yes,
you
ma'am.
are making the wrong guess, then the non-deterministic, there is no way of stopping the non-deterministic Turing machine. Here, in deterministic Turing machine, you definitely know. So you are guaranteed that this symbol exists. So you definitely know that this is going to stop after L square steps. But here you don't know whether you're going to stop after a certain number of steps. It is possible that you take infinite time. But if you are making the correct guess, you are doing much better than the deterministic Turing machine.
Yes, ma'am.
Yeah. Okay, so let's stop over here. I have one more, we had one more question. I'll just read it out and you can think on your own. So basically you're given an undirected graph in the following manner. This undirected graph has n vertices and the edges of the graph are given in row major order, meaning row, everything in row 1. So the adjacency matrix is written down in row major order. So suppose it was 0, 1, 0, 1. And if my adjacency matrix was, so these will be 0, 0. If it's 1, then you are basically writing this down as 0, 1, 1, 0 after the hash. Okay, so this basically corresponds to this particular graph. Now the question is, a Hamiltonian cycle is a cycle where every vertex is visited exactly once, and it's a cycle. So suppose you started with 0, then at the end of, you visit all the n vertices and you come back to 0. Each, if you just look at the edges of the Hamiltonian cycle, each vertex has degree exactly 2. So the question is, can I determine using a non-deterministic Turing machine, can I determine whether G contains a Hamiltonian cycle or not? This is an NP-hard problem. First of all, this is an NP-hard problem. It's a hard, if you don't know what NP-hard is, it's a very hard problem to solve. It's not always necessary that G contains a cycle. So you look at a tree. That tree will never contain a cycle, forget a Hamiltonian cycle. So it's not necessary that G contains a cycle. Your job is to design an algorithm for a non-deterministic Turing machine that determines whether G contains a Hamiltonian cycle or not. This is the encoding of G, and you can assume that you have constantly many tapes. You can assume that your tape head can stay stationary. You can assume all the other equivalences that you've seen. You can assume all that. And you then have to determine the running time of the algorithm polynomial in N. Okay, so I'll leave at this.
Ma'am, actually in the second question, which we were discussing, that Q1.
This one, yeah.
Yes, ma'am. So, ma'am, can you again explain what the encoding is? Like how we are exactly encoding the configuration?
So we saw this last class, right? Or not? So did you not see this? So suppose you have an encoding. What is an encoding? What is a configuration? You give me the state. You give me what is written on the tape. So I'll also include a right-hand marker just to be safe. And you include the position of the tape head. Now this I can encode as follows. So suppose I have W1. So this is W1 up to Wn and then Wm. Let's say, and I have Wn minus 1, Wn plus 1. What I do is n minus 1 q Wn plus 1 Wm. So my claim is this string is an encoding of this configuration.
Okay, ma'am, I got it. Like there are no, n. Okay, yes.
Yeah.
Yes, ma'am.
Fine.
Yes, ma'am.
Okay, so let's stop here. There was one more exercise that you had to solve. You can do it on your own, and maybe at some point towards the end of the course we can discuss any doubts that you have, or you can send us emails, whatever is comfortable. Okay.